Hello. Today we'll be talking about a very exciting topic, and that is the entropy of a black hole. So let's talk about what this even means. So an entropy is when you have a lot of microstates associated with one macrostate. So if you have your entropy at a certain energy would just be pretty much proportional, some constant times the number of states with that energy. So when we think of a black hole, okay, what's a black hole? It's pretty much all it is a region of space, which if you cross, so it's a surface along the space, and then if you inside of the surface, this is called the event horizon. And the black hole is defined by the space inside the event horizon, and if you cross the event horizon, you can't get out. So that's all a black hole means. After this, I'll talk about how to get a black hole. But for now, let's just think about what does it mean to have many microstates for this macrostate that we call a black hole. Since black holes only have mass, charge, and angular momentum, it could have angular momentum and charge, but definitely has to have mass. So yeah, what does this mean? So we'll get something very interesting and more importantly, very deep. So, okay, let's just say you have some mass, like the planet Earth, we have the Earth, which much bigger than the black hole, but this is not, I'm not drawing for scale, it has some mass m. So in order to get the, in order to form a black hole, all the mass must be compressed in a region less than r, with a radius less than r, given by this squared. So for the Earth, so if we plug in the mass of the Earth here on this side, the radius of the black hole would just be like 1/4 of a dime. So just imagine the whole Earth being squished down to just 1/4 of a dime, and that will give you a black hole. So it's pretty extreme situation you call a black hole. But anyway, so once a black hole happens, right now we have all these states, like I'm swinging my arm with so many degrees of freedom, but once it gets to the black hole, everything just falls in and we all just see just nothing, just a space that could absorb things. So we have the surface area. This is going to be an important quantity, so let's talk about this now. The surface area of the black hole is just 4 pi r squared. Usual geometry, nothing out of the ordinary. So what Hawking did, this is Hawking radiation. This is why he's famous and made it on The Simpsons and such. Aside from having a cool voice as well. Pretty much this black hole, it not only has mass, but he says it has temperature because it radiates. The black hole is radiating at a temperature that goes something like KT, HCQ, pi GM. So that's the temperature of the black hole. And what does it mean to have for the black hole to have a temperature? What does it mean to have space radiate particles? So the general notion is that an antiparticle and particle get created on the surface of the horizon. The antiparticle falls in. One of the particles goes in, one of the particles goes out, and this outgoing particle, because normally what happens is if you have a small region of space, an antiparticle and particle get created and they immediately annihilate each other. It's happening all around us, even in the space between me and this blackboard, a lot. The space between my eyeballs, everything, your fingernails, this is happening. So, yeah. So anyway, so it looks like the particle is radiating, and you can see here that the smaller the mass is, the hotter it is. So, you know, if I became a black hole, I would be a really hot black hole compared to the sun when it becomes a black hole, because the sun's much more massive than I am. So, okay, so we have a temperature, so it's radiating. A more detailed calculation would be just, you know, tracing out the quantum states that go in, and then you get a thermal state. So that's how he decided it was temperature. He just didn't pull this out of thin air. This is pretty legitimate. So the next thing I want to talk about, okay, how do you get the entropy of the black hole? So we have a temperature, we have an energy, and now we can calculate the entropy. Recall that the entropy is just defined by this. So we have this relation, dE equals T ds. And now our energy is given in terms of the mass. So remember we have E equals mc squared, dE equals dm c squared. So plug this into here and plug the temperature in. What we get c squared dm equals hc cubed 8 pi gm 1 over k ds. And then if we bring this on this side and we integrate, so we integrate both sides, bring the mass on this side. What we're left with is we get something c squared m squared 4 pi g h bar, and then I'm just going to put c down here because we had a c cubed and c squared, and then this gives you the entropy. Okay, great. So we have the entropy of the black hole. Putting this in much more illuminating terms, we could use the fact that the area of the black hole is just so that 16 pi gm c squared, and then what we're left with something that looks like we could write the entropy in terms of the area. And then, okay, so this is squared. So we need to divide by g. We need to multiply by c. Is that right? Oh no, c to the 4th. So you have to multiply by c cubed. We're going to divide by h bar. And then we have to divide by 4. Now, here comes our, okay, so we have entropy, so entropy is somehow related to the area. That's kind of interesting. What's more interesting is we have this this term, which we have that's just the Planck length squared, GC3. So we have 1 over 4 A of the Planck length squared. And for those of you who don't know what the Planck length is, can you see this, Chef? Yep. All right. So for those of you who don't know what the Planck length is, that is allegedly the smallest piece of space that that space makes sense. So this is the smallest area. This is about maybe 1 times 10 to the negative 35 meters. So after this area, our concept of space doesn't really make sense, and this is where string theory comes in. The strings are about this length scale, so then it can't probe less than this, but something called D-branes can. So anyway, this is very, very exciting. So what is it saying? We have this area of the event horizon, and then it's divided up we divide, so we take the area and then we divide it by all the Planck lengths. So the entropy is pretty much counting how many Planck lengths do we have. So now we have a lot of, now if we assign some degrees of freedom to each Planck length, you know, one degree of freedom, we get the entropy. We get something that makes sense. We get something, and we have these microstates kind of emerging from these Planck lengths. But this degree of freedom, like, you know, like what's the degree of freedom of these bits of pretty much space on the horizon of the black hole? Yeah, we'll get to that next time. We talk about string theory because that has a lot of interesting. String theory has an interesting interpretation. So thank you.